Aleksa, you ready?
Yeah, I'm ready.
Okay. Our next talk is by Aleksa, Sarai, and it's about path safety in the trenches.
Yes. So, hello everyone. It's lovely to be back at FOSDEM. I haven't been for quite a few years because I'm stuck on the other side of the world in a penal colony you may know called Australia. But yeah, I'll be talking relatively quickly about some work we did in runc recently that affects a lot of projects, but is kind of particularly nascent for runc. And I'm also at this new company with a lender called Amutable. So runc, I'm sure all of you know what runc is. This is going to be a very, very quick power through these slides. So runc, as I'm sure you all know, is sort of like the entry point to doing most operations that are container specific on Linux, and basically the entire OCI ecosystem runs through runc or runc-like programs. And runc has this, in OCI, we have this specification which defines this particular JSON structure, which you specify what kind of container options you like. I'm sure all of you have seen this before. And with the JSON file, you do runc run and you can run containers. All very simple. So the thing I'm going to talk about today is path safety. And so I suspect most of you have actually already run into what I call regular path safety in this talk, with some interesting bits. But the bit about strict path safety is something which I've been working on for quite a few years, and is something that is non-obvious when you first run into it, and it's very, very frustrating when you have to fix bugs related to it. So regular path safety is like the very classic time of check, time of use attack that you have with any kind of file system operation. Paths are just strings, so when you operate on a path, the path can get swapped out from underneath you. This is the classic, I want to sanitize a path problem, and you can't sanitize paths because if you sanitize the path, somebody could have changed it after you've sanitized it. And so like the classic example, there are lots of classic examples you can have, but you have some /rootfs, which is owned by an untrusted process. They can mess around with any of the files in there. So if you have an administrative process on the host that is like a container runtime that is trying to operate on these things, it can get tricked into opening random files it doesn't expect. And I want to point out, a lot of people think this oh-no-follow thing protects you. It doesn't. Oh-no-follow is extremely limited in what it protects you against. And in particular, in this case, if Etsy is a symlink to somewhere on the host, it doesn't matter if host is not a symlink, because oh-no-follow only stops host from being a symlink, not anything else. And basically, almost all of the classic VFS APIs have this problem. So you would think this problem has existed since Unix existed. It existed since before Unix. Surely this is a problem that doesn't happen very often. So this is a list of CVEs which are in the ones that I could think of when I was making this slide. You could easily make 5 slides or 6 slides that are just lists of CVEs about this kind of problem. It is an incredibly, incredibly common problem even today. And so this is really not a new problem, but we still keep running into it. So in 2019, I worked on this thing called OpenAD2, which is a system call that you can run on Linux. This is no longer new, it's quite old now. But what this allowed you to do is, in addition to the regular OpenAD interfaces, which let you operate on file descriptor, like directory file descriptors, you also have this resolution flags thing, so the resolve thing, which lets you control resolution. And so what this allows is it allows you to control aspects of how the entire path is resolved. And so I would say the vast majority of programs on Linux should be using at least one of these options. So either you want to use resolve in root, which is a kind of like chroot, but it only applies for that particular open call, and it has some additional protections that chroot doesn't have. Resolve beneath is kind of like chroot, except if you try to jump out of the root, you get an error rather than it being scoped like a chroot is scoped. This is a FreeBSD kind of API that actually, funny enough, I took inspiration from the FreeBSD API, and then they took inspiration from the Linux API for this. But yeah, and then resolve no symlinks is basically better oh-no-follow, so it actually blocks symlinks for any path component. You can still escape with absolute paths, which is why you want to do more than that. But these are incredibly useful things, and I find myself using them all the time now. The one thing, though, is that OpenAD only solves one problem, which is opening files. Now, it turns out this is actually sufficient for most programs because Linux has these, and not just Linux, the existing POSIX too, has these at system calls like make_dir@, and link@, and so on and so on, which let you operate relative to a file descriptor. And so as long as programs are written to primarily operate on file descriptors, not paths, you can actually protect against these issues basically entirely. So here's the example, one of the examples from before, but using the OpenAD2 and the path-based stuff. So for open operations, you just, rather than using, so you open the rootfs, this is a trusted directory. The directory is trusted because it's owned by the host, and then you use resolve in root, and then you just use regular open flags like you would everything else, and this protects you against these kinds of race attacks. The more complicated case, this is just one example, the more complicated case is if you want to do something like make_dir, because make_dir doesn't take resolve flags. What you need to do is you need to open the parent directory, and then underneath it, you just open underneath it. This is safe because make_dir does not follow trailing symlinks, and because there's no slashes in the path, this is safe to do. And you then do this for every single app system call and every VFS thing you're interested in. For older kernels, which when I first started working on this was a more pressing issue. These days, older kernels means like 7-year-old kernel, which some people are running, but less nowadays. Though it also should be noted that because OpenAT2 uses this structure thing, some systems block it with seccomp. Systemd blocks it with seccomp for its own usage, and some people block it with seccomp because seccomp currently can't filter pointer arguments. So effectively, they don't trust that we might add a backdoor to it, or like not a backdoor, but like a problem with it in the future they couldn't block. Anyway, point being that there is this old school way of doing it, which is rather than using the kernel's facility for doing these saved lookups, you can use opath to like emulate lookups in user space. This is quite finicky and a little bit annoying to get right, but it is something you can do. Some systems have done this in the past, and the key thing is that this is basically swapping out the OpenAT2 bit. The rest of your program still needs to use file descriptors for things. And usually you end up having to use this proc self-fd thing, which is this thing called the magic link, which I'll talk about in a little bit later, but usually it depends on this for validating that you are opening the files you want. Systemd does this in chasat for its own operations. Go last year added os.root, which does this in a more complicated way, and has a couple of limitations that I'm not a huge fan of, and libpathrs, which is a library I wrote. So libpathrs is a Rust library I wrote, which basically provides all of the main file system APIs, but within a root operation stuff. And it's written in Rust, but it has CFFI interface that you can use from Go and Python. I have Go and Python bindings. And now, the work I'm talking about here last year, you may have heard we had some security issues in runc. And so this work I've been working on for a while, but to do the security update, we couldn't just require you use Rust to fix the problem. So I ended up porting the core bits of the code you needed to Go. This is kind of a little bit funny because libpathrs started as a Go library that I was going to use for runc, and then I thought, other programs I needed, so I rewrote to Rust, and I rewrote to Go for this pathrs-like thing. So that was a little funny, but yeah. And the nice thing is that this library, it supports OpenAT2 and opath, and it supports a bunch of other new kernel features, but it transparently it doesn't use them if they're not supported. So this is the CAPI example where, it's rather than using OpenAT or whatever, you just use open root to get a root FD. You can also just use it's all file descriptor based, so you can just use the regular file descriptors if you like. And then, pathrs in root, do whatever. It's pretty easy to use. And then in Rust, I'm not going to go through this in detail because I don't have much time, but the Rust API uses like actual structures in Rust, but like the basic API is the exact same idea. You have a handle which is wrapped in a structure, and then you can operate on it individually. If you want more information, you can look at the docs for libpathrs. So that was regular path safety. Strict path safety is more annoying. So previously when we were looking at operating on random files, you don't actually care, as long as the file you end up operating on is within the routerfs, you don't really care which file it is, because an attacker can also swap the files around. We're assuming the person has privilege over the entire directory, so they could replace the file with whatever content they wanted anyway, so it doesn't really matter. As long as the file's inside the container, it doesn't really matter to you which file you get, because you can't trust it implicitly anyway, because the attacker can write to any file. Unfortunately, this is not the case for strict path safety. So on Linux, a lot of administrative operations go through procfs, which is a file system. And so the problem is with this is that if you want to operate, for instance, proc self-exec is how you specify what LSM labels apply to you, so what AppArm or SLint labels apply to you. If you're writing to that file, you need to be really, really sure you're writing to that exact file. You're not writing to some other procfs file, or that you're writing to some dummy file that doesn't do anything. Because if you don't write to the right file, then you won't actually get LSM label applied to you. And the same thing applies to most procfs files. So procfs is the most critical one, and the key thing here is that if someone makes a procfs that is fake, so it's either a temporfs that has fake files in it, or they mount on top of procfs from somewhere else, they bind mount a different bit of procfs on top of the procfs you care about, you can end up operating on the wrong files, and it's a big nightmare. So an example of something which would be strict path unsafety would be, I just open proc self-exec and I just write to it, and so on and so on. So actually every single one of these examples could cause a security issue if someone have it in overmount, and I'll give you some examples in a little bit later of how that happens. Now you think surely not that this is like not the real issue or whatever, but here are CVEs that we had in runc for this. There was a 2018 ones, and actually this was what initially inspired me to work on libpathrs and all this other work, because we hit this issue and then I realized, oh, this is actually a much bigger issue than it seemed at first glance. And then we had the issue from November last year that we also fixed. So the core issue here is that now you would think, okay, what can I do to fix this problem? What I'll do is I'll open /proc, and because procfs provides you the guarantee that the root inode of proc has a fixed inode number, it's 1, and you can check with statfs that it is actually procfs. Okay, fine, that's fine. I will open /proc, and I will check this, and then I'll use open@2 to make sure that I go to self-adder exec. And this resolve no xdev here is protecting you from overmount. So resolve no xdev reject going through mount points. So if you do this for regular files, this is all you need. So this problem is basically already solved. Very few programs do this properly, but this is a problem that's already solved. So if self was mounted over, or adder was mounted over, or exec was mounted over, you would reject the operation. Unfortunately, this is not all you need. You have these things called magic links. So magic links they look like symlinks, and if you have a laptop in front of you, you can look at proc self exe, and it shows me a link to the binary. But these are actually not symlinks. Symlinks are dealt with lexically. So in other words, you can imagine it's as if you take the link and you replace it with the contents, and then you continue doing the lookup. That's not how magic links work. Magic links are a kernel concept where basically all of them are in procfs, where when you do the open, rather than it being resolved lexically, the kernel knows what kernel object this link refers to, and it will pipe you through to the underlying object without going through regular path lookup. And this is very useful because it allows you to make quite useful security hardenings for various things. But on the other hand, it also lets you do container breakouts and stuff like that, because this stuff does not care about namespaces. You can open anything through a magic link. So to give an example, I want to reopen a file descriptor I have open. So I want to open proc thread self ft 123. And you would think, this is totally fine, I can do it because this is the exact same example as the regular file example before. But unfortunately, resolve no xdev will block this, because when you try to open the magic link, because this is on a different mount, most likely, because you go from procfs to some other mount, resolve no xdev will block it, right? Which is doing exactly what you want to do. So what you might then say is, I will open the fd directory no xdev, and then I will validate there's nothing mounted on top of the symlink, because if you didn't know this, you can actually mount on top of symlinks in Linux, which makes my life very fun. And so you're like, okay, that's fine, I'll just validate there's no overmounts, I'll just open the file. Unfortunately, this validating overmounts problem is actually unsafe, because if you are dealing with an attacker that can change the mount table from underneath you, then you can check it, nothing, and we're back to classic check time abuse attacks. Now, I will say, by the way, for this example, since Linux 6.12, Christian, I managed to convince him to block this, so you actually can't do this overmount anymore for this particular case, but there are other cases where you can do it. Besides, we need to solve this for old kernels anyway. So the solution comes in the form of the new mount API, which was merged 7-8 years ago now. However, I will say, it has NAM pages now. For those of people who have dealt with using the mount API, you had to read the kernel sources to figure out what the API looks like. Last year I wrote man pages for it, so finally you can actually read the documentation for how to use this thing. So hopefully more people will get to use it. But the key thing about this is that the new mount API allows you to create file systems without having to mount them to a particular directory. And because it's a file descriptor, nothing else can mess with it, and actually there are some nice protections that protect other people from propagating mounts into it and so on and so on. So once you have one of these, once you create a procfs handle this way, nothing else can interfere with it. So from this example before, we swap out the first bit with the open proc to create a new procfs instance. This is the simple example. In the more complicated example, you need to have a fallback for certain cases, but this is the basic example, where you create a procfs handle, which is a direct file descriptor to a directory like anything else. But the nice thing is nothing can overmount it, and now this validate no overmount stuff is actually totally safe to do, because nothing can overmount it other than your own process. And so this is the way you would do it, and there are other things you have to do that are also kind of annoying, but I made an API for this in libpathrs. So in libpathrs, if you just say, I want to open this procfs file, it will do all this awful stuff for you, and you just get to operate procfs the way you like. And it works on new and old kernels, and it has additional protections for a bunch of other stuff that I don't have time to get into. It also has a Rust API, which again, I'm not going to get into now, but yeah, it's kind of a very similar idea. The one thing to note is that you can make a procfs handle that you can cache for some usages and so on and so on. But yeah, so now some of you are probably thinking, and I've been asked this every time I give a talk or talk to anyone about this, is like, hang on, why do I care about any of this, right? Like only root can mount. Like why on earth would you care about someone mounting on top of proc? Well, unfortunately we're dealing with runc here. And one of the core problems we have with runc is that runc actually does not currently have a threat model. So one of the problems we run into is that Kubernetes and Docker and Containerd and Podman and et cetera, they all like to provide users with lots of flexibility about what they can configure. And because we don't have a fixed threat model, sometimes they allow users to configure things you wish they wouldn't configure. And that includes mounts, because if you do a volume configuration for a container, you've just configured a mount. And so every single time, and we have to provide volumes to people. So this means that mounts are very much in the picture of things that an attacker can control. So, and also some people allow people to run containers, unprivileged people to run containers in their systems because they assume that the container runtime will block malicious things, so we have to protect against these things. This is something I want to work on, and I've been speaking with some runc maintainers about doing a proper threat model, but at the moment there's no proper threat model, and every single vulnerability we have to do on a case-by-case basis. And the key thing to actually note is that because of this, a lot of vulnerabilities in the past decade with runc, most of them have been basically misconfiguration bugs, but the problem is that a regular user on a system using Docker or Containerd or Podman or Kubernetes could misconfigure it that way. So even though it was strictly speaking a misconfiguration, we have to treat it as a security bug. And one thing that really irks me is that people still don't use user namespaces. However, Kubernetes, I want to thank Rodrigo, Kubernetes, in the next release of Kubernetes, will have user namespaces like a fully supported thing for containers. So hopefully, soon, we will live in a world where everyone uses user namespaces because it's crazy to not use user namespaces in containers. Like, it's completely insecure. Anyway, I'm going to do a very quick pop quiz. This will have to be lightning round because we're running out of time. So I want you to put your hands up. Okay, how about this? Put your hands up if you think that what I'm about to show you is or is not a vulnerability. No, is a vulnerability. So, is this a vulnerability where I disable all the namespaces for a container? This is the easy one. The answer is no, because if you just disable all the security options, obviously it's not a vulnerability. Okay, I bind mount / so my host file system into the container. Is this a vulnerability? Yeah, some people say yes. Okay, so the thing is that if Docker allows you, so the problem is that for some people, I mean, this is a bad idea. I'm not saying this is a good thing to do, right? But the problem is that this is a management decision that Docker makes or Kubernetes makes about what you can do. From runc's perspective, this is just a misconfiguration. Like, you can configure any amount you like. I can't tell as runc what permissions you have, what RBAC permissions you have in Kubernetes, or what other permissions you have in Kubernetes. So from runc's perspective, this is not a vulnerability. Okay, how about this? I have a bind mount to some subdirectories. This is a vulnerability. It is a vulnerability. And in fact, this is the 2 CVEs we had in November. What I'm not telling you is that, so just to make sure we're clear, what's happening here is that I'm bind mounting some directory into some path / volume. How can that be a vulnerability, you ask? Well, the problem is that volume is actually a symlink to /dev, and there you actually have two processes. You have one process that is spawning this, and then another process is now creating fun files in some volume path. For instance, you make dev null or dev pts0 a symlink to proxy's core kernel pattern. And what happens is that in runc, we have to mask certain things in procfs because people don't use these namespaces, so you need to mask certain paths. And we mask them, so the first example, we mask them with dev null. So we bind mount dev null on top of the thing. But we don't use dev null from the host because there are security issues with taking file descriptors from the host. So we use dev null in the container. But if dev null in the container is a symlink to proxy's kernel core pattern, I've now bind mounted proxy's kernel core pattern on top of the files you like. And proxy's kernel core pattern lets you break out of containers because what you can do is you can specify a core dump helper, which is a binary, that the kernel will then spawn with full privileges on the host, completely unnamespaced. And so a similar problem applies to dev console and dev pts0. It's basically the exact same bug. So that's fun. We did fix this, obviously. So one of the things we did was we added much stricter validation of the inodes we use. So we now validate that dev null is actually dev null and not a fake thing. And it uses file descriptors to do the mounts, so it's safe against time check time of use. And same thing for PTYs. And basically all the mount point creation code in runc was moved over to libpathrs, or rather pathrs Lite, which is the Go version. And now most of the, almost all of the path stuff in runc is now file descriptor based, which fixes this and a bunch of other possible issues. And yeah, it turns out, wow, maybe you should care about regular path safety. And for consoles, there's this thing that I worked on many years ago called getpeer, ioctl, that actually makes a lot of things a lot more safe if you're making consoles. So now, next one. Is this a vulnerability? So what I'm doing is I'm mounting some fake file system on server /proc. Is this a vulnerability? Yeah, it is not a vulnerability. And because, well, It's not a vulnerability because, well, in this case, now that we've done this, we've actually blocked this, but, well? It used to be, all right. I would say if you had asked me 2 years ago whether I would consider this a vulnerability, I would say no. I would say that Docker should block you from doing this. In runc, we have code to block mounting on proc, but like, yeah, it's, okay, maybe half yes, half no if you want to be technical about it. And you would think, okay, is this a vulnerability? So this is the exact, so I bind mount proc1 shed over proc adder uphammer exec. Okay, now proc, for a bit of background, proc any pid shed is a file which just shows you like random information about a process, but you can write to it and it does nothing. So if you bind mount this file on top of proc adder exec, it's a procfs file. And actually in 2019, the fix we had for, sorry, I should say, in 2019 when we had these security bootloaders last time, the preliminary fix we had, because I knew that we didn't have this infrastructure yet, the preliminary fix was, oh, I open the file, is it a procfs file? If it is a procfs file, then I will write to it. The problem with this is that proc1 shed is a procfs file, it's just not the one you wanted, right? And so you end up writing something to it, does nothing, and now the container starts with no apphammer. However, this is not a vulnerability because runc blocks this, because we have a restriction of what you can mount on top of proc. For Aleksa reasons, there are some proc things you can mount on top of, but you can't mount on top of anything you like. However, let's look at slightly more complicated examples. The key thing here is that you have two bind mounts where you have a bind mount on top of foo, and then you have a bind mount on top of foo with a very suspicious looking path name, link thread self apphammer. Right, does anyone think this is a vulnerability? Yes, this is another vulnerability, and basically what's happening here is that you have some cache directory which is shared between two containers. It's the exact same attack as before. Oh yeah, he thinks it's a vulnerability. Oh no.
I mean, 5 minutes.
5 minutes, okay. Okay. Yeah, so anyway, this is a vulnerability because you can have this proc temp cache operator thing is a fun symlink to another target. Again, you can even get to proc shed. The best part is you can even symlink this to proc sysrq trigger, and turns out that exec docker default has a lot of fun characters to put into sysrq trigger, including basically this crashes your machine if you do this. So yeah, basically the fact that we were swapping between this link and proc basically allowed to bypass this check, and as before, call pattern allows you to escape from container. So the solution we came with was doing additional mounts. Again, we should have switched to the new mount API earlier. It's something I'm working on, but it's still not done yet. And yeah, the libpathrs, basically for all procfs writes in libpathrs, we now use, sorry, all procfs writes in runc, we now use libpathrs for them because it protects against these attacks completely. And it's, yeah. And also we went through every write path in runc to make sure there was nothing that you could misdirect for a write, which you couldn't. Okay, in runc, the things we need to do is we really need to move our mount infrastructure to using the new mount API. It's really quite insane we don't use it yet. And yeah, there's some audits I want to do. And also libpathrs exists in runc. Sorry, it exists as a Rust thing. Today you can actually build runc using libpathrs because pathrs Lite has libpathrs backend, but I think I want to get rid of this like intermediate Go thing. I just want to use the Rust thing because then runc can use it and other programs can use it, and it's much more robust than the Go version because the Go version is kind of designed to be a minimal thing. The kernel stuff I can skip over because it doesn't really matter. There's some kernel stuff I want to do, not too important. And the one thing I want to say for everyone in the room is if you are writing any kind of program that has to deal with paths, which is probably any kind of program, you should at least use OpenR2 or libpathrs for regular path operations. And you definitely, if you're writing new programs, you should definitely write them in a file descriptor-based way because playing around with paths is just waiting for trouble. And if you ever need to touch proc, you really need to use libpathrs with the proc stuff, or implement it yourself if you like, but you have to really do that. And yeah, the key thing to keep in mind is that any syscall that takes a path name is potentially dangerous, especially if you're dealing with untrusted directories. Okay, questions?
3 minutes for questions.
Oh, thank you. My apologies if I talk too fast.
I think the smoke needs to clear from the speaking speed. Okay. I don't think there's any questions. How do you feel about other projects? Like, do most projects a lot of projects that deal with paths are aware of this? Like, not just libpathrs, but path safety?
No. So the problem is that most projects. So what I tend to find is that most projects, to be fair, runc was kind of in the same camp for this, is that they write a version that works fine, and they've thought of like a couple of possible attacks, and then each time they run into one of these problems, they end up hacking around that one particular instance rather than looking back and saying, actually, we really need to rethink how we do this sort of stuff. Yeah. I will say one nice thing about that's in recent years is that the Linux kernel has actually moved a lot more to file script-based APIs, and this is a huge, huge improvement to the way things were before. I mean, everything is a file, everything is a file descriptor, yes. So, all right. Okay.
Okay.
All right. I think that's everything.
Thank you so much.
Thank you so much.